Welcome to this explainer. Today, we are unpacking the exact mechanics of an absolutely foundational concept in C programming, adding elements to a linked list. We're going to see how the source material elegantly maps out the memory management and pointer rewiring required to pull this off. Let's get right into it. Here's our roadmap for today. First, the insertion landscape. Second, adding at the beginning. Third, adding at the end. Fourth, inserting at a position. Fifth, synthesis and memory. And finally, diagnostics and decisions. Okay, let's dive into section 1, the insertion landscape, and really map out this problem. So looking at our newly allocated node, let's call it Z, it becomes pretty clear that inserting a node isn't just about casually tossing data into a list. No, it's a literal physical rewiring process in memory. We're establishing a brand new link, effectively pointing from our new node Z to the existing node A. Imagine we have our original list, right, A pointing to B pointing to C. To add Z, we allocate the memory, and then we have to physically rewire the pointer so Z connects to A. It is all about controlling these connections. Now, this insertion landscape basically breaks down into 3 distinct methods, and they rank by difficulty. Adding at the beginning, that's our easy path, because we just point the new node right to the start. Adding at the end becomes our medium difficulty, mostly because, well, we actually have to find the end of the list first. And then inserting at a specific position is the harder path. Why? Because it requires some seriously delicate pointer management. You have to break a chain right in the middle and splice a new node in, without losing the rest of your data. Right, let's look at section 2. Adding at the beginning, the easy path. Let's walk through the physical metaphor for prepending. In our before state, our head points to node 20, which points to 30, which points to null. Simple enough. Now, to insert a new node, say node 10, right at the start, there are 3 critical steps that happen in memory. Step 1, we create the new node containing the data 10. At this moment, its pointer is just a huge question mark. Step 2, we take that new node's next pointer and aim it at the old first node. So 10 now points to 20. But hold on, we aren't done. Step 3 is absolutely vital. We have to update the head pointer itself to anchor onto our new node 10. The after state perfectly shows our brand new continuous chain, head to 10, 10 to 20, 20 to 30. Translating those visual steps line by line into a realistic C environment, we start out using malloc with size of struct node to actually allocate the memory for our new node. And please look at the absolute necessity of the validation block right beneath it. You must always validate that memory was successfully allocated. If you don't, your program is going to fatally crash for sure. Next, we establish the link. This points our new node to the existing chain before we go ahead and modify the head. Finally, the update, we reassign that starting point and crucially return that newly modified head back to the caller. So why exactly is this our easy path? Well, because it's incredibly efficient. Creating the node, setting the data, pointing to the old head and updating the head, that is exactly 4 steps every single time. That elegance gives it an O of 1 or constant time complexity. It literally doesn't matter if your list has 1 node or 1 million nodes. Prepending runs at the exact same blazing speed. Plus consider the edge case where the list is entirely empty. What happens? Well, head is null. Our new node's next points to null. The head becomes the new node. The result is head points to 10, which points to null. It works flawlessly without needing any clunky special if statements. Moving on to section 3, adding at the end, the traversal challenge. To add a node at the end, obviously we first have to find the end. And we do that by walking down the list. We're checking one specific condition over and over. Is our current node's next equal to null? Say current is at 10. Is its next address null? Nope, it points to 20. So we move our magnifying glass over to 20. Is 20's next null? No, points to 30. Move to 30. Is 30's next null? Yes. The exact moment we hit yes, we stop. Now our current pointer is firmly planted on the last node, 30. Finally, we just set that last node's next pointer to our new node, 40, which itself points to null. Okay, back in the code, looking at the appending traversal engine. Notice the setup. We set up our new node, instantly assigning its next pointer to null, because obviously a node added at the end will always point to null. Notice the empty list catch here too. If the whole list is empty, we just return the new node immediately as the new head. But here's the most crucial part for the traversal engine itself. We absolutely must use a temporary pointer. We say struct node current equals head. This is a vital shared best practice. If we used our original head pointer to walk down the list, we'd overwrite our only reference to the start of the list, literally losing all our data. So the while loop simply says, while the next node isn't null, advance the current pointer to that next node. Now, because we actually have to walk the list, appending definitely comes with a cost. This is linear time, or O of n. To put that into perspective, 10 nodes take roughly 10 steps. 100 nodes take 100 steps. 1,000,000 nodes? Yep, 1,000,000 steps. You have to walk through the entire list to find the end. But listen, the critical warning to look out for here is the loop condition. The correct code checks if current.next equals null. If you accidentally check if just current equals null, forgetting that little arrow next, your loop is going to step right past the last node and fall off the end of the list straight into null territory. That makes insertion entirely impossible, and will almost certainly crush your program. Which brings us to section 4, inserting at a position, the harder path. Okay, I want you to look closely at this really delicate rewiring action. Let's say we want to insert node 25 at position 2. That's right between node 10 and node 20. Our current pointer has successfully parked at node 10. Think of the physical metaphor here. You have to grab hold of the new rope before you let go of the old one. Action 1, we take our new node, which is 25, and point its next to where our current node is pointing, which is node 20. You absolutely must connect the new node before you break the old chain. If you do action 2 first, pointing node 10 to 25, you completely lose the address to node 20, and the entire rest of your list floats away into memory forever. Connect first, then rewire. Notice the pretty elegant index 0 fallback we have here. If the user asks to insert at position 0, we simply route the data to our existing insert at beginning function. I mean, work smarter, not harder, right? But down in the for loop, look at the condition, I less than position -1. We are deliberately stopping one step early. This ensures our current pointer lands on the node immediately before the insertion point. And finally, those bottom lines execute that precise safe swap we just talked about. We attach the rest of the list to our new node, and then we anchor the current node to our new node. Alright, section 5. Synthesis and memory, pulling it all together. Looking at the complete main.c synthesis, this clean structure allows us to dynamically build out the list by calling our various insert functions. And looking at the console output, it proves it's working flawlessly, dynamically building out the sequence 30 to 20 to 25 to 10 to 40 to null. But please notice the critical detail here. You must assign the return value back to the head variable. If you just casually call the function without updating head, the new starting point gets calculated inside the function and then is immediately thrown away, meaning your list will remain completely empty. At the very end of our main function, we called freeList. Now this is the unsung hero of memory management. Every single time we used malloc, we essentially borrowed memory from the system. We have to give it back using free. But look at the while loop. We create a temporary pointer to safely hold on to the current node for deletion. This frees up our main current pointer to safely advance to the next survivor. Then and only then do we actually call free on that temporary node. If you just called free current directly, you destroy the pointer to the next node, causing a massive memory leak because you lose the rest of the list forever. Okay, final section, section 6, diagnostics and decisions, troubleshooting code. So what exactly happens when things go completely wrong? Well, in C programming, things don't just gently fail. They crash, they leak, they break in incredibly spectacular ways. Honestly, troubleshooting is half the job. This diagnostic matrix maps out the absolute most common failures. If your head is somehow unchanged in the caller function, your mistake is likely forgetting to return the new head. The fix? Just ensure you update the head variable with the function's result. Now, if your program crashes with the pointer stepping off into null, you probably used the wrong loop condition for an end insertion. Explicitly make sure you check if next is not null. If you get a nasty segmentation fault on the very first insert, you likely didn't handle the empty list scenario with explicit checks. And if your system just slowly runs out of memory over time, yeah, you've got memory leaks. Always validate your malloc returns and always use that free list disassembly line we just learned about. Knowing when to use which method really just comes down to synthesizing time complexity. If you need to build a list in reverse order, say reading a log file backwards, use insert at beginning. It's O of 1 constant time for every single item, which is just lightning fast. But if you need to build a list in the exact same order you are reading the data, you have to insert at end. Even though it costs O of n linear time to walk the list each time, it preserves that sequential order. Keep in mind, inserting in the middle or at the end will always cost you O of n simply because of that necessary traversal. Distilling all of this down to the absolute bare metal logic gives us this ultimate quick reference cheat sheet. At the beginning, point new to head, update head, bam, O of 1. At the end, walk while the next node isn't null, point the last node to the new node. That's O of n. At position, walk one step short of your target, do the delicate pointer swap, also O of n. And please, engrave this always checklist in your mind. Always check the malloc return value. Always return the new head when it changes. And always handle the empty list case. No exceptions? You've officially mastered the fundamentals. You know the code, the memory management, the O notation, and the common pitfalls. So, now that you control the links, what complex data structures will you build next? Stacks? Queues? Graphs? The foundation is entirely yours. Thank you so much for joining me for this explainer. Don't forget to like and subscribe to my channel. I always drop videos every week on my channel, and happy coding.